Instead of doing that, now you introduce an extra term which depends on the previous value of so vt. And so when you calculate the theta, you basically use vt to do that. So the value, so I can work it out, I can kind of show it to you mathematically. But what that does is that this gamma introduces sort of an exponential weighting. So it's a moving average. So what it does is it weights the things that are, it weights the last update more than any of the previous ones, but it does include the previous ones. So it's an exponential decay of the previous one. So this value is typically a value between 0 and 1. So the way to think about it, if you're to calculate it mathematically, with so this is sort of like it's sort of an intermediate value, but you have vt minus 1 minus the delta theta xy, right? So, oh, and that's forgotten eta term, which is your learning rate. Okay, so the gamma in this case is your momentum. So when you kind of like plug it in, so for example, suppose you start with v1, and v0 is equal to 1. So v1 is equal to simply actually v0 is equal to 0. So it's simply minus eta. Actually, it's plus eta v theta j xy. So that's your v1. And then what you do is your v2 is equal to gamma v1. I'm just going to call this for the time being some basically zeta theta. So I don't have to write it out, but it's basically equal to this piece there. So v2 is equal to gamma v1 times that, and then what you have, if you plug it in, it's just simply, you see this is theta 1, and what you end up seeing is that this is simply moving that over there. So then v3 equals gamma v2 plus theta prime. And so if you plug that in, you end up with gamma v1 plus, and gamma v1 you can also expand out and so on. But what you notice is that this gamma, when you multiply that in, it increases exponentially. So which means that further back you go, the older the term, the further it essentially decays. The way it weights the oldest values the lowest, and puts more weight on the most current backpropagation. So the overall effect is to smooth. It's a smoothing function. What you have is that, suppose you have, this is your data, this is your training data. So one way is, so the original function that you're trying to map is simply a Gaussian. So with momentum, you have a kind of a smoother curve. So this is basically, and so what happens is that if you vary the momentum, you vary the smoothness. So if the beta is very high, it's kind of hard to see there, but if the beta is very high, then you essentially see that it's pretty smooth. If the beta is very low, you see it's very noisy, and the beta, and beta somewhere in between, it is smoother but not so smooth. The issue with momentum is that it will eliminate some of the random factors when it converges, which is a good thing. But basically, so for example, if you look at stochastic gradient descent, you're introduced, it's a pretty random decay. If you introduce momentum, then what that'll do is smooth that by a bit. So the challenge with momentum is the issue there is that when you smooth it, you're going to be you're actually more likely to get if it's rough, you don't really know how much it's decaying. So if you look at, for example, this, with a smooth function, you actually see it's getting closer to kind of what you want. When it's really rough, you don't know which direction it's going to go. It's like it can go up, it can go down. So it can move further away from the right answer to move closer to the right answer, because it's modeling noise in that respect. So what you end up doing is you have the momentum. It can basically cause if you increase the momentum, it kind of smooths out how you actually get to the minimum, which essentially makes it, gets you a chance to calculate the real derivative. It'll give you a better chance of getting the real derivative. The advantage is you get conversions faster. The disadvantage is that you could miss a local minima, and actually, because of depending upon the size of the the momentum that's actually happening there. So another issue is that typically you don't deal with just one parameter. So you're not just converging in one parameter, you're converging in many. Like a typical neural network has billions of dimensions in some sense. If you think about the weights, you're essentially calculating the derivatives across all of the weights. So when it converges, it's converging across a lot of different values. And the problem is that with momentum, it will converge faster in some directions than in others. And so you end up with you could end up seeing that it's bouncing a lot in one direction and not really converging there, but it might be converging in another direction, if that makes sense. Right? So basically, the upshot of it is that momentum results in a smoothing of the gradient descent. So instead of bouncing all over the place, it will smooth it down so that you have you're not modeling noise so much. You don't have as much noise in the descent function, which is a good thing. So, however, if you overdo momentum, it's possible that you'll kind of overshoot, and you're not going to actually calculate the correct minima as well. So the reason why it's called momentum is this is sort of just I kind of like it or don't like it depending upon my mood. So if you have this is your MSE, and this is your parameter that let's say it's only one parameter, then you could have something like that. So what happens is that if you have like you're decaying, you could get down to that. And what momentum does, it can give you a kick to kind of like push you into the next, so that you're actually decaying down to the next minima. And whereas so the advantage of that is that you can potentially, with a high momentum, you can avoid maybe falling into a specific minima and actually like explore it outside. And so that's an advantage. So that's kind of how I think about it. Okay. So another thing that you'll hear about is ensemble learning or cooperative learning. The way to think about it is, instead of building one model, you build a bunch of different models. And what you're trying to do is, if assuming that you get a positive response, what is the probability that, so this p-value, by the way, is conditional probability, and the way to read it is the probability that if this condition is reached, then this condition is true. So if you have, so the way to think about it is the probability that given that there's thunder, what is the probability that there's lightning somewhere? And that's probably very close to 1 at that point. But this is the way to read it, is that given this is happening, what is the probability that that is happening? It doesn't necessarily imply causality. It just simply says that there's a connection between them. So the way to read this is that given a positive identification by your model, what is the probability that it's really Marilyn Monroe? And so let's say model A is about 0.7, model B is about 0.6, and model C is about 0.75. Then basically when you calculate the overall probability, you can actually combine, it's kind of like a voting method, and you end up with a 91% probability if all of them are positive. So the ensemble learning method is, you can basically use that to increase the confidence in your response. There's a second one which is called sequential ensemble learning, which is it's called gradient boosting. So sequential ensemble learning is where you take a model, you essentially get a weak model, you put it into a second model, and then you put the response to a third model. And so every time you do that, so you basically you feed it into another model with an estimator H, and then what each of these models will do is it would correct its predecessor. So the way to do that is that it in fact it'll essentially increase the probability that the overall model is correct. So this one is basically using it in parallel, and that's basically sequential approach to actually calculating that, to increasing the confidence in your answer. So gradient boosting is a really good way to, if you don't have enough data in your training set, using gradient boosting, it'll increase the likelihood that you're going to get the right answer.